Hi all! Suppose you have a bunch of different colors of paint. You can mix them and get new colors. Sometimes you can mix some of the colors to obtain a color you already have. For example, mixing red and yellow to obtain orange. In this case, you would not have needed to buy a bucket of orange paint, as red and yellow would do. In a way, the color orange is dependent on the colors red and yellow. For vectors, we can say something similar. If we have a bunch of vectors, v1, v2, etc., we say they are dependent if we can write one of these vectors as a linear combination of the others. For example, as v3 equals 2 times v1 plus 3 times v2, we say that the vectors v1, v2 and v3 on the slide are a dependent set of vectors. To see whether v1, v2, v3 is dependent, we would have to check three equations. v1 equals a1 v2 plus a2 v3, v2 equals a3 v1 plus a4 v3, and v3 equals a5 v1 plus a6 v2. Note that all three equations can be rewritten in the same form. Indeed, they are equivalent to an equation of the form c1 v1 plus c2 v2 plus c3 v3 equals 0. Therefore, we define linear dependence as follows. A set of vectors is linearly dependent if there exists a non-trivial solution to c1 v1 plus etc. plus cn vn equals the 0 vector. Recall that a trivial solution is a solution where all the ci equals 0, which always exists. If there does not exist such a non-trivial solution, the vectors are called independent. Let us see what happens in R2. If we have just a single vector v1, to see if v1 is dependent, we consider the equation c1 times v1 equals 0. Non-triviality means we exclude the obvious solution c1 equals 0. And as c1 is non-zero, we can divide by it and obtain that v1 must be the 0 vector itself. For two vectors, life gets more interesting. v1, v2 is dependent if there is a non-trivial solution to c1, v1 plus c2, v2 equals the 0 vector. In the table, we consider the four cases whether or not c1 and c2 are 0. We exclude the case where both are 0, as that would be the trivial solution. If c1 is 0 and c2 isn't, then v2 must be the 0 vector. So we can have any vector and the 0 vector. The case c2 equals 0 and c1 is not gives v1 equals 0. In the final case, we can rewrite the equation as v1 equals minus c2 over c1 times v2, so v1 is a non-zero multiple of v2. That is, v1 and v2 point in the same direction. This last case is more typical, as it is not that often that you run into the 0 vector. Anyway, in all cases, two vectors are dependent only if they lie on a single line. And vice versa, if two vectors lie on a single line, then either one of them is the 0 vector, which lies on all lines, or both are multiples of each other, so they are dependent. In class, you will learn that three vectors in R2 will always be dependent. Consider the example on the slide. Given that v1 minus v2 plus v3 equals 0, the three vectors are dependent. And in this case, we can write every one of these three vectors as a linear combination of the other two. However, it is a common misconception that this is always true. Indeed, the three vectors on the right are dependent as they satisfy the equation 2w1 minus w2 plus 0w3 equals 0. However, in this case, the third vector, w3, cannot be written as a linear combination of w1 and w2. Come to class to learn how to determine whether a set of vectors is linearly dependent.